Thank you very much for the opportunity. Thanks, Anish, for inviting me. Maybe it's a good opportunity to congratulate Professor Dani. We are all grateful for your countless contributions, and as you will see from the talk, your ideas and infrastructure for the playgrounds in which we all play are just still keeping to appear in nowadays research, and personally I'm just grateful for having this for being exposed to these ideas and being able to continue your work, and thank you very much. Okay. So today I'm going to talk about some very fundamental concepts in geometry of numbers or Diophantine approximations, which I kind of think of as the same subject. And the nice and somewhat soft interplay between ergodic theory and those areas. So the first thing that I want to do is to discuss these notions of what do I mean by best approximation. So the part one of the talk would be intro and results. Introduction. Okay, so what is the game that I want to play? We are looking at, so we fix a dimension d greater or equal to 1. So the discussion will even be interesting if we're discussing numbers in R, but I will mainly focus on d greater or equal to 2. So fix d greater or equal to 1 and a norm on RD. And the basic thing that we want to do, so for a vector theta inside RD, we want to define the sequence of so-called best approximations of theta. So what is that? Let me define it first using a picture and then maybe write a formula. So what I do is that I draw a copy of RD, which will be horizontal normed space. So this is RD equipped with the norm. You can think of the Euclidean norm or the sup norm if you want to keep it concrete. And then I add one extra dimension. So this would be ED plus 1. I add another dimension. And I form a vector theta with an extra coordinate 1. So I lift theta from RD to RD plus 1. And I consider the ray R plus times theta 1. So at some point I don't want to carry out the arrow above the theta. So I look at this ray, and what I do is that I travel along this ray, and I look for integral points closer and closer to this line. So assuming that theta was somewhat irrational, if I project this line onto RD plus 1 mod ZD plus 1, so this line wraps around. I don't want to assume totally irrationally on the torus, but definitely it comes back close as I wish to the origin modulo the integers, which means that I'll find, as I go along this line, I'll find arbitrarily close integral points. And the game that I want to play is that I want to climb along this line and record the best approximations. So the integral vectors in ZD+1 are layered in layers. Okay, so I have the height 1, height 2, height 3 integers, and in each level, say in level 1, I choose the closest integral vector. So it's going to be some p, 1, and then maybe in the second layer I don't see anything better, but in the 7th layer suddenly I see a p, 7, and in more general a p, q that wins over the previous approximation that I saw. So the sequence is actually defined inductively. So we define inductively a sequence. So let me call them Vk of theta. And Vk would have, this would be an element of ZD+1. And I will write it as a Pk. Pk is a integral vector in ZD. And then there is the height Qk. And it's defined inductively by Q1 equals 1 and P1 attains the distance between theta and ZD. So in the first layer, I just choose the closest integral vector. And then if I know V1 up to Vk, then Qk plus 1 is the minimal Q bigger than Qk, such that the distance of Q theta to ZD+1, to ZD, sorry, is strictly smaller than the distance between Qk theta to ZD. Okay, so if I found my kth best approximation, P, K, Qk, this is a vector that wins over all previous lower approximations. Now I continue until the first time I see something that gives me a lower distance to this line, lower horizontal distance to this line that wins over the previous one. Okay, so this is the sequence of best approximation. This gives us, for any vector theta, it gives me a sequence of integral vectors in ZD+1. It's easy to see that almost by definition, they are primitive vectors. I cannot, so the GCD of the components must be 1, because otherwise I would be able to divide this vector by something and get something that wins over it, okay? So they are actually primitive vectors, primitive integral vectors of ZD+1, and they are naturally attached to the vector theta, or to the direction theta, 1. And geometrically and from the point of view of the Belinfante approximation, they are extremely natural to consider. The only non-canonical thing about this definition is the norm. I chose a norm on RD, which allows me to measure those distances, those horizontal distances to the line. And this is a choice. I need to make a choice for the norm, and things become dependent on the norm. The only case where the norm is, where I don't have a choice for the norm is the dimension 1. And indeed, in dimension 1, what I get from this construction is the convergence of the continued fraction expansion of theta. And this is kind of a God-given object. It's not depending on any choice that we make. But it seems that in higher dimensions, this is a highly natural object to study. And the subject of the talk is to look at this sequence of best approximations for a direction theta, and first of all ask or kind of suggest natural objects that you could attach to those best approximations. What features do they have? What questions can you ask about them? And maybe analyze how do these aspects of best approximations behave along the sequence. Okay, so that's the goal. Okay, so what are the objects associated to best approximations? Okay, so the first thing that I want to do is maybe again draw so this is my horizontal RD, and this is my direction R plus times theta 1. And let's say now assume that kind of RD is multidimensional, so that we could have some richness in this picture. Suppose I have an approximation VK. I want to first consider the direction from which it approximates the line. So it can come up in the two-dimensional case. It can be on the right or on the left. And those of you who see the connection to continued fraction expansion know that they alternate between left and right always. Here in higher dimensions, you should expect the kind of spiraling phenomena that the best approximations would approximate the line from all directions. So let me define the object that I need here. So I want to consider this horizontal displacement vector. It will go to 0, right? So I have two options. Either I renormalize it to be of length 1, or I renormalize it in a meaningful way such that it will be in some ball, okay? So that option captures more information, and this is what I'll do. So I'm going to define the displacement of data with respect to the kth best approximation to be what? So I have the vector pk minus qk theta. That's this vector. It's in RD. And now I want to blow it up by qk to the power of 1 over d. That seems to be you will see in a moment why this is the correct scaling that will put this vector in some ball in RD of radius R naught, where R naught is going to be some universal, specific radius. Okay, so this is it's sometimes called the reminder or the displacement vector, which tells me where do I approximate the ray from which direction, and also somehow it captures the not only the direction but also the quality of the approximation. Another quantity that I want to it doesn't erase well. Say again? This one? Okay, another quantity that I want to, or not quantity, this one, this was a vector, okay, which gives me some geometric information about the approximation. Now I want to attach a certain less trivial geometric object, but I find it very interesting, and this is the directional lattice. So along the way, I'll explain the notation. So for So we can project, so maybe I'll call it directional lattice. And what do I want to do? What I want to do is the following. I want to take the lattice ZD plus 1, and I want to project it onto the horizontal copy of RD, with kernel being the kth approximation. Okay, so VK is an integral vector, and this is a point in the space of lattices. And then I rescale the covolume to B1, and this is a point in the space of lattices in D dimension. So I've used a bit of notation. Let me define it. It's very hard to erase the board because of the water. Okay, so pi RD W is the projection onto RD in direction with kernel W or RW. And if lambda is a lattice in RD plus 1, in D plus 1 space, such that that vector W is in lambda, then this projection, since the kernel of the projection actually meets the lattice, then the projection of lambda onto RD is a lattice in the horizontal RD. And that's just the space of lattices. This is SLDR mod SLDZ. And by this bracket, what I mean is that I rescale the covolume to be covolume 1, or just I take the homothetic class of that lattice. Okay, so that's an object, and I call it the directional lattice because this is how, if you stand on the horizontal plane and you look at the direction of VK, if this is VK, then all the lines parallel to VK look like points to you, and ZD plus 1 looks like this thing. So this is the directional lattice, okay? So the second object that I want to attach to a best approximation vector is this directional lattice. And maybe the third object that I want to attach to it. So these are two, I would say, geometric aspects of the best approximations. Now I want to consider an arithmetic aspect, and one could consider this thing in several ways. One simple way would be just to say, okay, I'm going to take the residue class of my vector VK modulo some integer m for a fixed m. Or if I don't want to fix an integer m and I want to consider all residues at once, then I'm going profinite, and I will consider the integral vector VK as an element of the profinite completion of Z. So let Z hat be the product of all p-adic integers, p prime. So this is the profinite completion of Z, and Z hat to the M is just the m-fold Cartesian product of Z hat, and I can think of, oh, not M, D, and I want actually D plus 1. So Z hat D plus 1 contains VK of theta. Okay. And what happened here with these three objects is that you see I've taken a primitive integral vector which happens to be a best approximation, and I've associated to it three objects that reside in nice topological spaces. Two of them are compact, the ball of radius R node in RD, this completion, Z hat to the D plus 1, it's a compact space. And well, this is not a compact space, but this is a probability space, nice locally compact manifold. And now I can state the results. So let me start with the with the following. So we have associated to each best approximation vector Vk of theta, a triple. So it's the displacement, maybe I'll write it, Qk to the 1 over d times Pk minus Qk theta, that's the displacement. And then I have the directional lattice, phi Vk Rd of Zd plus 1. The way Zd plus 1 looks in the direction of Vk from the horizontal plane. And finally, simply Vk, but thought of as an element of a compact group. So this is in a product space, Br node in Rd times space of lattices in Rd times Z hat to the power of D plus 1. I'm not yet adding. I'm adding the information. Yeah. If you tell me that Vk lies super close to the 0 element in Zp, in the p coordinate of this of this product, then it means that all the coordinates of Vk are divisible by a huge power of p. So I managed to capture arithmetic data on the vector of best approximation by knowing where is it situated inside Z hat. Okay, so far I didn't say nothing. I just set the stage to state the results. Okay, and now come the results. So we have two kind of, I didn't say, so this is everything that I'm saying is joint work with Barak Weiss. So funny enough, 6 years ago, I was in Goa in a similar conference that Anish was organizing, and I gave the same talk. So this is not a new result, but it has new aspects to it. Oh, it's really horrible to erase the board here. So what happens? What happened in this six years period from that talk is that the results got amplified a bit. So you will see if any of you have been in that talk, then maybe you can recognize the improvements. And second of all, that there is a preprint on the archive. It took us many years to complete this writing process. Somehow, I hope you will see from the description in this talk that the results are soft and elegant. but somehow writing accurate proofs is a mess because of technical issues. So the paper is actually much too long in some sense. But hopefully after this talk, you will have maybe motivation to open it and suffer through the details. Okay, so what is the first theorem that I want to state? So this is a statement about almost any theta. So, and this holds for any norm on RD. The norm, I remind you that the norm defined to us the sequence of best approximations. So for Lebesgue, almost any theta in RD, the sequence, maybe let me call it star. The sequence star equidistributes so let me write the space again, B R naught RD times XD times Z hat D plus 1. I will explain in a moment what do I mean by equidistribute, because this is a misleading terminology. Equidist towards towards a probability measure. Let me call it U best. And it has a certain structure. I want to call it, it's of the form mu infinity times UF. So F is the finite, these are the finite places, and this is the infinity places in some sense. So mu infinity is a probability measure on the ball BR naught RD times XD, which is absolutely continuous with respect to the natural measure. So this product space has a natural measure on it. The XD supports the SLD invariant Haar measure projected to XD. So there is a unique SLD invariant measure on the space of lattices, and the ball supports Lebesgue measure. So the product measure here normalized to be a probability measure. That's the kind of the uniform measure on this product space. And the measure that you get in this equidistribution process is absolutely continuous with respect to that product measure, but it is not a product of the two natural measures. But neither its projections to RD or XD is the natural measure. Okay, so there is some density. The density will be clear from the argument somehow, but the density is non-trivial. Okay, somehow, let's say in the space XD, the mass that the cusp gets is smaller than usual, if I'm not mistaken. Okay, so maybe I should comment about what, for those of you who are not familiar or familiar with this notion. When you have a locally compact second countable space like this product space, and you have a sequence of points in this space, then you can form the measure 1 over n sum k runs from 1 up to capital N, the Dirac mass at my kth point, xk. So this gives me a sequence of probability measures supported on bigger and bigger chunks of the sequence. And if these probability measures converge in the weak star topology to a certain probability measure, then we say that the sequence equidistributes towards that probability measure, which is the limit of those guys. Okay, so that's the meaning of the statement. And if I go back to I didn't finish stating the theorem. So for almost any theta, the sequence of best approximations gives rise to a sequence of objects in this product space. And this sequence, and this is a locally compact Hausdorff space, so we can discuss equidistribution in it. And the statement says that this sequence equidistributes towards a limit, and there's some description of the limit. I told you that the limit is a product measure. I told you something about the measure that's supported on the product ball times xt, namely displacement vector and directional lattice. I didn't tell you anything about the finite component. The measure mu f is the unique. So this is the natural measure. It's the unique SLDZ invariant probability measure. So this SLDZ is dense inside SLDZ hat, which doesn't act transitively on this space, but there is an orbit here which is called the primitive vectors, the norm1 vectors in ZD+1 hat. So the measure mu f is the unique SLD. You can add a hat here, SLDZ hat invariant probability measure supported on the it's a D+1, sorry, SLD+1 Z hat orbit of, say, E1. Okay, so there, all these primitive vectors are in the same orbit, and yeah. Okay, so going back to Anish's statement or question regarding this finite coordinate, if I ignore the geometric aspects and only consider the arithmetic aspect, then what I'm saying here is that for almost any theta, the sequence of best approximations behave completely randomly in terms of arithmetics. So it equidistributes inside a certain compact group, but actually not in the whole compact group, because it cannot. It's, by definition, these are primitive vectors, so they are stuck inside a single orbit of SLD+1 Z hat, and there they equidistribute. Okay, so yeah. So what I said earlier, that my vector would all of its coordinates will be divisible by a huge power of p. This is impossible, right? Because it's a primitive vector. But if I want to see some residues, eventually I'll see them. Okay, as long as there is one primitive vector that gives me these residues. Okay, so this is the statement of the theorem regarding almost any theta. And now I want to complement this with a result which was not existing back in Goa, and we have it now. And this is a result, maybe to give a background somehow. So ergodic theory, in many cases, ergodic theory, when we apply it, it gives us something like, for almost any starting point, something nice happens. Okay, like what we see here. But it almost never gives us information about concrete examples. This is why Ratner's theorem is so so powerful because Ratner's theorem gives us something about any orbit of a unipotent group. And this is basically what leads to the strength of unipotent dynamics. So in that respect, the following result is unique, and it says the following, because I'm going to say something about a particular theta. So let let theta, theta 1 up to theta d in RD be a vector such that the span of 1 theta 1 up to theta d, so span over Q, let me denote it by K, is a totally real number field. So some algebraic thetas. So totally real number field of degree d plus 1. Okay, so this is my assumption about theta. Then the sequence star. So now I'm considering the same objects, but for algebraic thetas. And well, maybe your first guess might be that an algebraic element will behave randomly, unless it has a very good reason not to behave randomly. And in this case, it has a very good reason not to behave randomly. So the statement says that the sequence equidistributes to a measure. This time the measure depends on theta. So let me call it mu best, but with the parameter theta. So this is a probability measure on this product space, BR node RD times XD times Z hat to the D plus 1. I can add a primitive thing here because everything is stuck inside a primitive, inside this, this orbit of SLD Z hat, SLD plus 1 Z hat. So there is a limit, that's the statement. And to complement that, moreover, I want to kind of stress that it's a very different limit than the limit that we saw earlier. So the statistics of the observables that we are interested in, displacement vector, directional lattice, and the arithmetic behavior of the best approximant is strictly different than the almost sure behavior. So moreover, the projection of this measure to each of the coordinates is singular with respect to the natural measure, the previous the natural measures. So it's also kind of a feature of the proof. You see where it is supported, and it's supported on some finite union of submanifolds. In the ZP case, it's a kind of a algebraic submanifolds. So it's it's really a different phenomenon. Okay. Maybe I should add here, and so remark. I should have added in the statement. Maybe so the norm for the algebraic case, there is some technicality appearing in the proof. And we need the norm to be either the Euclidean norm or the infinity norm. Okay. I hope to be able to explain where is this technical thing needed. Okay, so I finished part one of the talk of introducing the objects and stating the results. Any questions? Yeah, so I'm saying that they are singular with respect to the smooth. Yeah. So they are supported on submanifold. Okay, perfect. Now I want to tell you about the proofs. So that's the second part of the talk. For the almost any theta, in each projection is absolutely continuous. And for that one, it's supported on some manifold. Okay, so how do we do that? About the proofs. So the first stage is basically the standard viewpoint of the Dani correspondence, or the link between the finite approximation and dynamics. And this is to kind of shift do a change of coordinates to instead of working with the lattice ZD plus 1 as a fixed lattice with which I want to approximate lines, I want to maybe it's just maybe the introduction was too harsh. It's not. I could work with ZD plus 1, but somehow it's more conceptually convenient to me to think of the direction theta 1 as fixed. So I want to change the coordinate that it will move to the vertical axis, and the lattice will change, and the randomness will be a randomness in the lattice. So step one is change coordinates. So we apply. We want to move from the line spanned by theta 1. I want to move it to this line. And ZD. So which matrix does that? It's I'm applying U minus theta. It's identity D by D identity minus theta 0, 1. So this kind of moves this line horizontally. Things slide horizontally until the line is vertical, and ZD plus 1, which resided here, and I used to use these lattice points to approximate the slanted line, now becomes a lattice I call lambda theta. It's U minus theta times ZD plus 1. Okay, and now what's the game? Instead of going along this line and approximating it with integral points, now I'm going across the vertical line, and I'm looking for lattice points which are of the lattice lambda theta, and they approximate a fixed vertical axis. Okay, so that's maybe not this is just a change of viewpoint, but it's a conceptual one which helps me. And I think of it as kind of moving the randomness to the lattice, because now theta is inside the lattice. Okay. So I can kind of amplify the discussion and say, okay, I'm interested in the vertical axis, and giving a lattice, not necessarily of this form, I can start walking along this axis and define the sequence of best approximations to that line. And now I want to give you like a geometric observation of how to detect when a vector is the best approximation. So step two is an observation that says how to detect best approximations. And I'll do it with a drawing. So what was the procedure? The procedure was to go along the line and wait until I see a vector which its distance to the vertical axis wins over the previous distances. What this means, the fact that it's winning over the previous ones, means that this cylinder is free of points. Okay, that's an if and only if. If there is a point here, it didn't win. If there is no point here, it wins. Okay, so let me, for a vector V, let me define the cylinder CV to be the set of x's in Rd plus 1, such that maybe the d plus 1 coordinate of xd is less than the d plus 1 coordinate of V, and the norm of the projection onto Rd of x is less than the norm of the projection onto Rd of V. So this is like a formal definition of this cylinder. Each vector defines a cylinder, okay? And the cylinder is a symmetric set like this. Okay, and so V in lambda theta is a best approximation if and only if lambda theta intersected CV is just 0 and plus minus V. So the cylinder is free of points. Okay, now where does dynamics come into the play? Instead of seeing a bigger and bigger cylinders, I want to kind of shrink them and renormalize them to be of height 1. Okay, so I'm going to use this standard 1 parameter subgroup. So use AT. So AT is going to shrink the vertical coordinate by a factor of t, of e to the minus t, and expand uniformly the first d coordinates to bring V to height 1. So for some reason, I want to see this vector at height 1. That's my normalization. Now comes Minkowski's theorem. So if this is the best approximation, and I bring it with this diagonal matrix to be of height 1, okay, so suddenly it sits here. So this is ATV, and this is ED plus 1. So this is a disk of height 1, and I can calculate the radius of this disk explicitly from the radius of this disk and the height, because I used a particular diagonal matrix to do that switch. And the previous lattice, lambda theta, didn't touch the interior of the cylinder. So the new lattice, AT lambda theta, doesn't touch the interior of the new cylinder, okay? And this gives me some bound on the volume of the cylinder, right? So it gives me a bound on the radius that I can see here, okay? And this is the R node from the statement of the theorem, okay? So choose R node so that the volume of what? Of the cylinder corresponding to the vector ED plus 1 when I add to it, when I move to the right, R naught times, say, E1 in the direction of E1, so that the volume of this is equal to 2D plus 1. And then the observation is that all best approximations must hit this the upper part of this cylinder. So let me draw this picture again. Now I'm looking at height 1, ED plus 1, and I'm drawing a cylinder or a disk horizontal to a horizontal disk of radius R naught, where R naught is chosen specifically this way. And what I see here is that any best approximation must hit this disk. Okay, let me call this disk dR naught. Okay. So what I'm going to do is I'm going to study the best approximations by, so this is the idea of the proof, or one of the ideas in the proof. Main, and it's very naive and soft, you must agree. Main idea in the proof is use or study the trajectory AT lambda theta and stop at times t such that AT lambda theta has a primitive vector in dr naught. Okay, so I'm kind of flowing, letting the dynamics take its place, and I'm stopping each time I see a lattice point hitting this this disk, and I'm claiming that okay, so you see the correspondence between best approximations and the heating times, and I'm claiming that the dynamics didn't change. At least, so I'm going to concentrate on the geometric aspects. I will comment at the end about the arithmetic coordinate in the statements. But if I'm just interested in the directional lattice and the displacement, here I actually, if you calculate which point of, so VK was here, and it hit after t seconds, it hit this disk. This is exactly the displacement vector that I was about to study, and also the way that the lattice AT lambda theta looks like when you look in that direction is the same as your original question about the directional lattice of ZD plus 1 in the direction of VK. So if I stop at those times and I consider the same questions that I started with, I see the same information that I had before. So, okay, so that's the idea. Now, what's how to make this precise, how to get such results in a precise way. So how long do I have? 8 minutes. Okay, perfect. So now I want to discuss the cross sections. Okay, so I'm going to be brief and draw a lot and write less. So what is this concept of cross section? You have a nice space X, and you have a flow AT on it, one parameter flow, and you choose a transverse to so some set S transverse to the action of ATs, and let's assume that we're in an ideal world where each orbit hits S infinitely many often in the future and infinitely many times in the past. And this way we can define a first return map. So a return time is a map tau from S to R plus, which tells me what is the time I need to flow until I hit the section once again. And once I have the first return, the return time, I have a first return map from S to S, which sends a point X in S to its next visit to S under the flow. Okay, and the point is that, so let me kind of be completely inaccurate and hide all the technical details, but to convey the idea, there is a natural correspondence between measures invariant under AT on the space X and measures invariant under the first return map on the cross section. And the correspondence between measures is quite explicit. If you know the measure on X, you can kind of give the measure on S, and if you know the measure on S, you can induce the measure on the corresponding measure on X. And also, it's not completely true, but not far from the truth, that if you start from let's say that the measure on X that I consider, the AT invariant measure on X, is actually ergodic, and I start with a point here that has an equidistributed orbit, or a generic point for AT on the full space, then its visits to the cross section will equidistribute with respect to the conditional measure on S. Okay, and this is basically what we are doing here. Behind the scene, you kind of see that there is some cross section here, right? I'm waiting until something hits something. I'm waiting until I see a primitive vector on that lead, on that disk. So that would be my cross section. Having lattices with a primitive vector on DR node, this would be the cross section. And then, if I was correct in what I said, a point in the big space which equidistributes under AT would hit the cross section in an equidistributing sequence on the cross section with respect to the induced measure on the cross section. Okay, so the results that I mentioned at the beginning, they follow the following thing. We write down the cross section explicitly. We expressed it now, and we calculate in a very specific way, and this is something I hope to show you in a moment, why this cross section is actually so successful. We calculate on the cross section the induced measure for, say, the Haar measure on the space of lattices. So xd plus 1 is my space of lattices. It has the Haar measure on it. Now I have defined to a cross section. It's actually a non-compact subset, but let me write it like this. And we will be able to write down explicitly the cross-section measure. And hence, since I know that for almost any theta, lambda theta equidistributes, and roughly speaking, if I didn't cheat you, then its visit to the cross-section will equidistribute with respect to the measure on the cross-section. So if I have a nice way to write this measure, I get a meaningful statement. Okay, so maybe I'll finish by just telling you what is so nice about this cross-section, which wins over other cross-sections. And this is another thing that I didn't mention. So this, there were prior works on the subject that used cross-sections and used the flow AT, but somehow they chose the wrong cross-sections in the sense that it was hard to write the cross-section measure. And here, it's very easy to write the cross-section measure. And let me tell you why is that. So I told you that my cross-section SR node would be the set of lattices lambda in X d plus 1, such that the primitive vectors of lambda actually contain, so lambda contains a primitive vector on the disk dr naught. Okay. So the point is that this set has a very nice product structure. So how do I get a primitive vector on this disk? It's a movement of ED plus 1. Can you describe all lattices that contains ED plus 1 as a primitive vector? So if H is the group that fixes ED plus 1, then it's not hard to see that the periodic orbit H times ZD plus 1, for example, or for what it's worth, any other lattice containing 0, 1, containing ED plus 1 as a primitive vector. So this periodic orbit is the set of all lattices containing ED plus 1 as a primitive vector. So that's one observation. But this is not my full cross-section. This is only lattices that contain ED plus 1 as a primitive vector. Now I need to move it. So I'm using the ball of radius R node in the group U to move ED plus 1 to a general position in dr node. So U is going to be this ID V01. This is what moves me horizontally. And this thing is not far away from the product. Okay, so I've acted on this finite volume orbit with this compact part of this transversal group, but actually it's not far away from the product, and this gives me like a natural product measure on the cross-section, namely Lebesgue measure on that ball times the periodic age invariant measure on this finite volume orbit. And it's not hard to show that this is exactly the cross-section measure. Okay, so, and this is why hitting the cross-section gives us this nice equidistribution statement. Right now, you may think, so this coordinate encodes the displacement vector, and this coordinate encodes a bit more information than the directional lattice. You could ask me here, oh, so why did you say that it's not a product measure? It seems to be a product measure, but recall that not all the cross-section detects best approximations. In order to see a best approximation, I need to know that I'm looking at a lattice such that the corresponding primitive vector defines a cylinder which is free of points. So this is kind of a subset of this cross-section, which when we hit it, we know that we have seen a best approximation. So this is the density, the characteristic function of the set is the density that appears in the theorem. Yeah, maybe it's a good time to stop here. I think I've explained some of what I wanted to.